Hello, and welcome back for the last lesson for chapter 5. This is over inverse trig functions. So we learned about inverse functions in chapter 4, and now we're going to learn about the inverse of the trig functions. So the arcsine function is defined as the arcsine of x is y if and only if x equals the sine of y. So we're essentially thinking the arcsine of a value is what x in radians could give me that ratio for sine, we would say. So the domain of the arcsine is a -1 to 1, and the range of arcsine is a -π/2 to π/2. So they're just opposite of each other for the sine function. And this is what the graph of the arcsine looks like. And then similar arc cosine works in the same way. So it's much easier if we just kind of talk through what it means. So if I said, what is the arc cosine of 1/2? I'm really asking myself, what value in radians would produce a 1/2 for cosine? And that would be the cosine of π/3. So for instance, example 1 says, find the exact value of the arc sine of 1/2. So I'm asking myself, what theta in radians gives sine theta equal to 1/2? That's the question I'm asking myself. And so we're going to go to our unit circle and say, okay, sine is 1/2 at π/6. It's also 1/2 at 5 π/6, but we're going to use the π/6. So this is equal to just π/6. Example 2 says, find the exact value of arc tangent of 1. So again, what theta in radians gives me a tangent of theta that equals 1? So that would be either π/4 or 4π/, either π/4 or 5π/4. Those are the two places where tangent is equal to 1, because tangent is sine over cosine. So that would be π/4. Composition of these functions should work the same as just like the composition that we learned in chapter 4. That if you compose sine with its arcsine, you just get x. If you compose cosine with its arc cosine, you get x. The same with tangent. So example 3 says, find the following, the arc cosine of 4π/3. So that means the arc cosine of cosine at 4π/3 is a negative 1/2. And so the arc cosine of a negative 1/2 is what radians would give me a cosine of equal to a negative 1/2, and that would just be 4π/3. So this is just taking the composition of arc cosine of cosine. So it's back to the 4π/3. Example 4 is a little bit different. It says, find sine of arc cosine of a -3/5. So I first need to find the arc cosine of a -3/5. And so when I think of a -3/5 and the cosine that would produce that, it would have to be in the second quadrant or the third quadrant where cosine is negative. So a -3/5 would be the adjacent is a -3 and the hypotenuse is 5. And so it's whatever this angle theta is, I want to find the sine of that angle. And so that means I need to find the opposite a so that I can find the sine of that. So that means I've got a squared plus a -3 squared equals 5 squared. So 8 squared plus 9 equals 25. If I'm solving for A, and I subtract 9 on both sides, take the square root, I find out that A must equal 4. It's that perfect 3, 4, 5 triangle. And so that means the sine of the arc cosine of a negative 3 over 5 is equal to 4 over 5. So in this case, I didn't actually need to find the angle per se. I just needed to find the sides of that triangle in that quadrant so that I could find the sine of that. And then example 5 follows on one of the examples. It is an extension of one of the examples in the book. It says when a projectile is fired with an initial velocity v sub 0 and an acute angle theta, the horizontal range is given by this formula, where g is a gravitational constant. It's what's pulling down at 9.8 meters per second squared. If a projectile is fired with an initial velocity of 80 meters per second, at what angle must it be fired in order to have a horizontal range of 550 meters? Express the angle in degrees. Okay, so the horizontal range of 550 is r. So we want to find the angle theta. They're telling us that the gravitational constant is 9.8. That's g. And our initial velocity is 80, and we have to square that, and sine of 2 theta. So I'm going to multiply both sides by 9.8, and then 80 squared is 6,400. And 550 times 9.8 is 5,390. Divide both sides by 6,400. And when I do that, I get this ratio or decimal 0.8422. So to find the sine of 2 theta, to get to this theta, I have to take the inverse sine of 0.8422. And that gives me 2 times theta. And I'm going to show you how to type that into right here. So I'm going to clear these all out. So it's usually on this main page here. If you type in the decimals for scientific calculator, and you only see sine, cosine, and tangent. If you click on this button right here where my mouse is, it says function. Then you have the inverse functions, and you can click on the inverse of sine and then just type in 0.8422. And we get the angle of 57.37 degrees is the double angle, 2 times theta. And if you take 57.37 and divide by 2, then theta is 28.69 degrees. Also make sure here that you have your angle your information is given in degrees, not radians. See where my mouse is? We want this to be in degrees. It switches back and forth. So that angle theta is 28.69. And that is the last of the lessons for chapter 5.